when you used to give input, and for the combinational circuit you need to give input and you get output. So whatever output you get depends upon this present input only. So this first layer, this combinational circuit with input and output, comes under combinational logic, and it has all the gates, the decoder, encoder, all mux and all these things comes under this. But when a circuit requires its previous state also, then memory comes into picture, and memory is something which depends upon the time. Memory depends upon the time, and your present state is stored in this memory, and the basic memory element is a flip-flop. One flip-flop is capable of storing 1-bit memory, and when I show here in this box memory, it may be 1-bit memory, it may be a bigger complex sequential circuit, but something which is capable to store the state of the circuit, and this also goes as input. So now this circuit will have input, and it will also have the state which is stored in this memory. So this circuit becomes a sequential circuit. So combinational circuit or combinational logic will not have flip-flop, but a sequential circuit will have flip-flop as well as combinational circuit. A sequential circuit cannot be complete without the combinational circuits in it. So this is basic block diagram of a sequential circuit, which shows that memory is coming into picture, and memory only is sequential component, and combinational circuit will have combinational component. And along with this, you should also know that there will be a clock coming into picture all this time. When you talk about memory, memory is always with respect to time. So you will have a clock coming into picture, and as you know, this complete one cycle is called as clock period. Clock period, or we can call it as clock cycle. Yesterday in the class I was telling na, so first clock cycle all P's and G's will be calculated. Second clock cycle your carries will be calculated. Third clock cycle carries and your P's and G's together will give you the output. So when I say first clock cycle, second clock cycle means this only. First clock cycle means this complete clock period. Second clock cycle means this complete clock period. Third clock cycle means this complete clock period. So clock becomes an important point here, because memory has to retain its memory for specific clock period of time. That is why it is important for you to know memory as well as clock period. Now, to start with, the first thing of your sequential logic is basic bistable element. Now, what do you mean by bistable element? What do you mean by bistable element? Basic bistable element. You know that digital logic depends upon two states, low state, high state. So either it will be at logic 0 or it will be at logic 1. So these two states are called as logic 0 and logic 1, and a memory can store this logic 0 or it can store logic 1. So that means what? It will have only two states to be stored. So that is why we say bistable element. Bistable means it will have two stable state. Two stable state means it will be either logic 0 or it will be logic 1. Now I am showing you two NOT gates which is connected to each other in this fashion. Output of one is connected to output of other. Output of one is connected to input of the other. So I will call this as gate 1 and I will call this as gate 2. So if these are the input and these are the output. Now let us see what does this mean. This means that, now all of you please understand these things carefully. If A is equal to 0, if A is equal to 0, this NOT gate will make Q equal to 1, right? if A is equal to 0, if A is equal to 0, Q will be equal to 1, and this 1 is fed back to this B, and B is also 1, and 1 will be complemented with this NOT gate 2, and Q will remain 0. Now can you see that if A is equal to 0, A, Q, B and Q bar will remain in this state forever. Forever means till power is supplied to this circuit. A will remain 0 forever, Q will remain 1 forever, because this is connected here. 1 will remain here forever and this 0 will remain here forever. This all started, and when Q is equal to 1 means we are storing a logic bit 1 in this. We are storing a logic bit 1 in this. In the same way, if I want to store a logic bit 0 in this, what can be done? If I want to store a logic bit 0, what can be done? Quickly. I think I should take your test tomorrow itself.
Ma'am, you should make A1.
Yeah, I have written that now. Thank you. If A is 1, Q will become 0. And this 0 will be fed back to B. B will remain to be 0. And Q bar will become 1. So now you can see this 0 is stored with this bistable element. So if you want to store a 1, the red color thing remains true. If you want to store a 0, blue color remains true. Now you all know that a shorted NAND gate, if I say that this NAND gate is there whose input is shorted, it behaves as, what does shorted input NAND gate behaves as? Is my question now.
Not gate.
Not yet, ma'am.
Yeah, correct. So shorted NAND gate behaves as a NOT gate. So this 1 and 2, whatever I have shown with this basic NOT gate, can also be showed with this universal NAND gate. So this universal NAND gate is connected in the inverter form. It is behaving as inverter. So the same circuit, I am replacing this NOT by shorted NAND. And now this will behave as a basic bistable element. So if somebody asks you that make a basic bistable element using universal gate NAND, then this is the circuit. And what will be the circuit for NOR? What will be the circuit for NOR, basic bistable element? What should I do? What should I do for NOR
Can you
gate?
repeat the question, ma'am?
I am saying that with NOT gate, I made a basic bistable element as shown on the screen. With the NAND gate, this is also a basic bistable element. So these are three circuits. First circuit, second circuit. I used a NAND gate in a shorted form to behave as basic bistable element. If the same thing I want to do with NOR gate, what shall I do? For NOR gate, what shall I do?
In the same arrangements above.
Yes, we need a same arrangement. Same arrangement means your input should be shorted here also. Why this is true? Because a shorted input NAND or NOR gate behaves as an inverter circuit, inverter or NOT gate. That is the reason that I can use this circuit also as a basic bistable element. So now you got to know three types of basic bistable element. One using a NOT gate, second one using a NAND gate, and third one using a NOR gate. So basic bistable element is nothing but a 1-bit memory cell. You should understand this circuit very carefully, because this circuit will be used again and again and again. So this is nothing but 1-bit memory cell. This is 1-bit memory cell. So this 1-bit memory cell, 3 types of 1-bit memory cell we have seen, which is also called as basic bistable element. All the 3 circuits are same. Any doubt in this? Can we go on to the next topic?
Yes, ma'am.
Okay, so let us, whatever I do, you have to keep on copying along with me. Okay, so this is your first, smallest, simplest circuit of sequential logic, that is basic bistable element. Next, we will see something called as SR latch, and I will be explaining one by one. There are varieties of SR latch, and you people should not get confused with that. Before I start, I will simply list out. Number 1, you will be doing SR latch using NOR gate. Then what I will do, I will convert that SR latch in some form that it converts to a NAND gate, and then it is called as S bar R bar latch. That will be your second circuit. First circuit is SR latch using NOR gate. Then second circuit will be S bar R bar latch using NAND gate. Okay. Now in market you do not get this S bar R bar thing. So what do? We convert this S bar R bar by having some more NAND gate, and then we call it as SR latch using NAND gate. Okay, so one by one you will be seeing 3 circuits, and you should understand these 3 circuits very properly. So try to understand each bit of it. So now second thing what we are going to do is SR latch using NOR gate. Now I want you people to remember the operation of NOR gate. Okay, then only you will be able to understand. I know that people mug up and they do not understand the working properly. I don't want you people to be in that category. So let me make the circuit first. In the circuit, what do we have? We have again your 2 NOT gate, the way we had in basic bistable element, but we will not short the 2 NOR gate here. One will be connected to R, means reset input, and the other one will be connected to S, that is set input. S for set, R for reset, and the other input is fed back from the output of the adjacent NOR gate. So this is your SR latch using NOR gate. Now you have to remember one thing. Q is connected to the gate with which R is input. I always tell this so that people do not get confused. R and Q are part of same NOR gate. Why I am telling this? Because when NAND happens, no, then this changes. We will see that anyway in today's class only. So let us start with SR latch using NOR gate. Now, before I go into the details of this, I want you people to remember the logic circuit of, or the operation of a NOR gate. What is NOR gate? You have 4 options. And what is 0, 0 output for a NOR gate? Tell me fast. What is the output of NOR gate for input?
1.
Yes.
1, ma'am.
Yeah, 0, 0, OR is 0, so NOR is 1. And same way, it is 1 for first 3 cases, right? Fourth case is 1, 1, so 1, 1 is a 1 for OR, so 0 for NOR. So what you can see is, these 3 cases output is 1, only 1 case output is 0. Now, let us understand very, very carefully what happens in case 1. Now, please remember that you should not mug this up, you should understand this. Case 1, when I am trying to set the flip-flop, I am...
Ma'am,
Yes.
NOR gate truth table, there'll be 1, 1 and 3 zeros, no ma'am?
0 0, correct. 0 0 is 0, so
0,
1.
0 and 1 and the rest 3 are zeros.
Yes, right. This is correct. Thank you very much. So because the 3 input, second, third, fourth is 1 1 1 for OR gate, so NOR gate will become 0 0 0. Good, thank you. So now let us see our case 1. In case 1, when set is 1, okay, when set is 1, we will not bother what is the previous state, because you can see in the NOR gate circuit that if any one of the input is 1, output is forced to be 0. Can you see this? When one of the input is 1, without bothering about the second input, output is forced to be 0. So if this second NOR gate, if this second NOR gate is having S equal to 1, it will not bother what is coming as the other input for this second NOR gate. It will force Q bar to be equal to 0. Right? Why that is so? Because second, third and fourth options in the NOR gate shows that if any one of the input is 1, output is forced to be 0. So when S is equal to 1, Q bar is forced to be 0. Q bar is forced to be 0. Now, if Q bar is forced to be 0, then what happens? This 0 goes here. This 0 goes as the input of the first NOR gate. Now, when the first NOR gate is getting a 0 here, then what is happening? It will have an option of seeing the reset. Now, reset will decide what will happen here. So, for this case, I am assuming that S is 1 and R is 0. Now, you see what will happen. When S was 1, Q bar was forced to be 0. Reset is also 0. So 0 and 0 will make Q as 1. Right? So your R is 0 and Q bar is 0. So these are the first NOR gate inputs. So seeing the truth table, what you see, if first NOR gate input is 0 0, output becomes 1. So then Q becomes 1, right? So without, see, in set what did you see for NOR gate 2? It did not bother about what is there as the second input. So that means what? Whatever is the previous state, Q is our previous state, no? So without bothering about our previous state Q, this second NOR gate forced Q bar to be equal to 0, which in turn along with R equal to 0 made Q equal to 1. Is this case clear? When set is 1, R is 0, without bothering about the previous input, your flip-flop is, or your latch is set. SR latch is in set mode. What do you mean by set mode? Set mode says that Q is equal to 1. This is called as set mode. Is this case clear? Can I go on to the next case?
Yes, ma'am.
Next case says when I am trying to reset the flip-flop. Okay, I am trying to reset the flip-flop. Same story will repeat for the first NOR gate now. All the story, whatever happened for second NOR gate, the same story will repeat for first NOR gate. Now let us see what happens. Now when R is equal to 1, when R is equal to 1, it will not bother about what is there at Q bar and it will force Q equal to 0. So when R is equal to 1, Q is equal to 0, again that is forced. Again that is forced without bothering about what is coming with the Q bar feedback. So when Q is forced to be equal to 0, then what happens? When Q is 0, you can see, when one of the input is 0, output can be 1 as well as 0. So it depends upon the other input also. So when a reset is 1, I am assuming that set is 0. Okay. So now when set is equal to 0, so what will happen? You will have your Q as 0, which is forced. Q is 0 and set is also 0. When Q and set both are 0, 0 input, so what is my input? Input is S is equal to 0 and Q is equal to 0. These are my second NOR gate inputs. Second NOR gate inputs will make my Q bar equal to 1, right? Q bar equal to 1. So when R is equal to 1 and S is equal to 1, Q becomes 0 and Q bar becomes 1. So SR latch is in reset mode. SR latch is in reset mode. So what do you mean by set mode and what do you mean by reset mode? Set mode says that Q is equal to 1 and reset mode says that Q is equal to 0. Reset means it has resetted. Q is 0. So Q is 0 in reset mode and Q is 1 in set mode. These two cases are clear.
Yes, ma'am.
Now case 3. Case 3 when S and R are 0. You all know that if I have two inputs, there will be four possibilities. Two cases I have already seen. Now I am seeing the third case, that is S equal to 0 and R equal to 0. Now you should understand this case very carefully because this is only the memory state. This is only the memory state. Now when we talk about memory state, we will have to look into both the cases. Both the cases means if your memory is storing 0 or if your memory is storing 1, we will have to see both the cases in S equal to 0, R equal to 0 case. Why we have to see? Because you know that in case 1, as when S was 1, it was not bothering about the other one. In case 2, when R was 1, it was not bothering about the other input. But here 0 0, when inputs are 0 0, it need to bother about the other input to get me the output of these NOR gates. So that is why when S equal to 0 and R equal to 0, there is no forcing happening to this NOR gate. Forcing happens only when one of the input is 1, then only forcing happens. So now forcing is not happening. So in this case, we will have two cases again. First case we will see initially when Q is equal to 1 and Q bar is equal to 0. We will see this case now. Now let us see when Q is 1. Okay, all of you see this very carefully. When Q is 1, my second NOR gate will get one of the input as 1, one of the input as 0. So when one of the input is 1 and one of the input is 0, what will be the output?
0.
0.
0.
Q bar will be 0. So what you can see that the first case when Q was equal to 1 and Q bar was equal to 0, I will start with the second NOR gate only because I am happy to work for the NOR gate which gets 1 as the input. So one input is coming in the second NOR gate. So your second NOR gate gives Q bar equal to 0. And now this Q bar equal to 0 goes to first NOR gate feedback. R was already 0 and Q bar became 0. So 0 and 0 will give you Q equal to 1. So first NOR gate inputs are 0 and 0. So it gives Q equal to 1. So can you see? You started with Q equal to 1, Q bar equal to 0. You ended with Q bar equal to 0, Q equal to 1. That means nothing is changing, right? You did this one circle, feedback and all that. Nothing changed. That means what? 1 remained 1 and 0 remained 0. So this is called as 1 bit memory. 1 bit memory to store what? What it has stored now? To store a bit 1. It stored this bit 1. So this is the case when it behaves as a memory which is storing first bit 1. It is storing bit 1. Now let us see the other case. Other case we have to see under case 3 only, and other case says that if q is equal to 0 and q bar is equal to 1. Now what will happen? Which gate working I should see first? Q equal to 0, q bar equal to 1. Which gate working I should see first or second?
First one, ma'am.
First one we should see, because that is getting a 1 as the input. It is easy to work with the NOR gate when input is, one of the input is 1. So I will take first NOR gate. So now the first NOR gate is having one input as 1, because q bar is 1 now. So what will be the output? Output will be forced to 0. So now first NOR gate will give q equal to 0, because one of the input is 1 and other input is 0. So it is a 0 and 1 will give a 0 only. Now with that what will happen? You got a 0 here. 0 will be fed back, and second NOR gate will get two inputs as, second NOR gate will get two inputs as now 0 and 0. So that will give me q bar equal to 1, right? Same story is happening, just the gate is inverted. So you started with q0, q bar 1, you ended with q0 and q bar 1. So this is the case of 1 bit memory. This is the case of 1 bit memory to store a 0. To store a 0. Is this clear? This memory state is most important to explain during your exam also. Okay, this is clear. Now let us see case 4. Case 4. Case 4 is simplest to understand, because in the beginning only I have told you something called as, case 4 says s is equal to 1 and r is also equal to 1. Now what is happening? You have seen till now, if any one of the input is 1, it forces the output to be 0. So what you can see here, both the NOR gate will force the output to become 0, right? Both the NOR gate will force the output to become 0, and both will be giving 0 as the feedback then, but R and S will be forcing the output to become 0, and 1 and 0 will, see, your q and q bar should be complement of each other as the circuit says. So when S and R both are 1 1, it will force the output, both the NOR gate will try to force output to become 0 and 0. Both the output as 0 and 0 is prohibited. It is not allowed. Why it is not allowed? Because the circuit says that it has to be in a complement state. So S equal to R, S and R equal to 1 forces 1 and 2 both gate to have q equal to q bar equal to 0, which is not allowed. That is why it is called as indeterminate state. Indeterminate state, because it is not allowed. This is not allowed. Okay. So this is your 4 cases of SR latch using a NOR gate. Now, is this clear to you all? Quickly,
Yes,
I will write here your truth table, okay, with respect to your S and R. Now I am writing a small truth table, or I can say concise truth table. Okay, so when S and R are 0 0, it is a memory state. It is a memory state. We can write it as no change, or we can write it as a memory state. That is your S equal to 0 and R is equal to 0. And I am writing output only as Q. Q bar is anyway complement of that. Even if I don't write, it does not matter. Okay, when S is 0 and R is 1, it is what state? It is what state?
Reset state.
It is a reset state and your output is 0 in this, right? Output is 0 in this. And what is the third case? Set 1, reset 0. So then it is in a set state. And set state says that output is 1. And last case is when both are 1, 1. This is the state which is not allowed. And then we will say that your output is not understood. It is not understood, or we can say indeterminate. 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 In one page only I had to cover, so it became little cumbersome. Bear with it. So this is your SR latch using NOR gate. If you have understood this very properly, I will do some small change and quickly the same circuit will become the circuit for S bar R bar latch also. Okay. Can I go on to S bar R bar latch now? I will do small changes here, which is called as logical change only to make you understand. Okay, that does not happen in real world, but to make you understand, I will use that. Okay, now all of you have this circuit in your notes, no? I will change the page. What I am trying to show you is S bar R bar latch using a NAND gate. Okay, so next is S bar R bar latch using NAND gate. Okay, now you people should understand this in proper serial order, so that later you should not say that something is there in the mind but not clear. It should be engraved in your mind what I am saying now. Okay, I am repeating the circuit so that you people should not get confused.
NAND gate, not NOR gate.
Yeah, I am changing this only to NAND. You will see what I am doing. For your reference, I am making this circuit again using the NOR gate again. This is the circuit which you saw in the previous page. Okay. And if you remember, can you tell me if I want to make a NOR gate from AND gate, or let me just put here, I am making a bubbled AND. Do you remember this? Bubbled AND is equal to what? What is bubbled AND equal to? Think and tell me.
Active low input, ma'am. Active low input and gate.
Active low, that is fine. I am asking about the operation. What is a bubbled AND equivalent to? What is a bubbled AND equivalent to?
And ma'am.
NOR gate.
NOR gate, ma'am.
Right. Bubbled AND is equivalent to NOR gate. Now for the students who are not remembering that suddenly how a bubbled AND gate is equal to NOR gate, I will show them how it is. You know that what is bubbled AND? Bubbled AND means I am trying to AND A bar dot B bar, right? This is only bubbled AND. Bubbled AND means what? It a complement of something is going into AND. So A bar dot B bar is a bubbled AND. And if you apply a De Morgan's law, joining the line and changing the sign, it becomes A plus B bar. So bubbled AND is nothing but a NOR. Bubbled AND is nothing but a NOR. So what I am doing, I am replacing this NOR gate by bubbled AND. I did not do any change in these two circuits, right? These two circuits are both same. These two circuits are same to each other. So NOR gate is replaced by bubbled AND because operation is same. Right? Now see what I am doing next. What I am doing next. This bubble is there, no? Whether you do a NOT here at the input or whether you do a NOT here at the output. Is it one or the same thing? Yes or no?
Yes, ma'am.
It is one or the same thing. So now I am making this circuit same as I am shifting this bubble. I am shifting this bubble to the output side. I am shifting the bubble to the output side. So can you see I have shifted this one gate input bubble to output of the Q bar side. Same way I will shift the bubble this side also. I will shift the bubble this side also. So both the bubbles I have shifted, right? And one of the bubble is there as it is. That I did not shift. Can you see? Did I do any change between this circuit and this circuit? This is circuit number 1, circuit number 2, circuit number 3. All the three circuits are same only. I did not do any change, right? So only I have shifted the bubble back to Q bar, shifted this bubble back to Q. So no change. Now, circuit number 3. Circuit number 3, again I am not doing any change, but only thing I am saying, R is complemented and put here, S is complemented and put here. Instead of putting that complement bubble, I will put that as R bar. Can I do that? Can I do that? Instead of bubble, I have written R only as R bar. I have written R only as R bar, and I did not do any change. I did not do any change. So circuit number 1 is equal to circuit number 2 is equal to circuit number 3 is equal to circuit number 4, right? And suddenly the circuit has changed from RS NOR latch to R bar S bar NAND latch. Can you see? Suddenly things have changed. Now what will happen? What will happen? The previous this thing I had shown, na, this also changes, na, with bar bar. So what will happen now? 1 and 1 will become memory state. 1 and 0 will become reset state. 0 and 1 will become 0 and 1 will become reset state, and 1 and 1 will become the 1 and 1 will become 0 and 0, and that will become the indeterminate state. So everything becomes ulta, right? Everything becomes ulta. So now this truth table will be little different. Now let me make a little neater truth table now. I will show that now what is happening. 0 and 0, which used to be memory state, becomes a indeterminate state. And 0 and 1, which used to be before reset state, is now a set state. A set state with a 1 output. And 1 and 0, before it used to be set state, but now it will be a reset state because everything has become opposite. And 1 and 1 used to be indeterminate state. Now it will become a memory state, and memory is nothing but same input, that is no change. So this is your new truth table for S bar R bar latch, right? This is S bar R bar latch. And what is the block diagram of S bar R bar looks like? You show here that it is S bar R bar, and you have a Q and Q bar. So your logic symbol looks like this. So this is all about your S bar R bar latch. Now in the market, it does not look good to have your input as bar and bar. We do not like that. So what is done? Here again you can see that your R in the gate which has R as input as Q as output. Slowly this is going to change. That is why I am pointing it again. Okay. Now R is connected to Q. Can you see? R bar is connected to Q. Now I am going to another circuit which is called as SR latch using NAND gate. Till now you saw S bar R bar latch. Now if I want to make SR latch using NAND gate, what do you think? What should I do? What do you think I should do? This is your last circuit for today, that is SR latch using NAND gate. SR latch using a NAND gate. What can be done? Tell me. You can see that first of all, you see that here you are having your R bar and S bar, right? You have your R bar and S bar. Now what I am trying to do is, I am trying to, instead of this bar, you can use a shorted NAND gate, right? You can use a shorted NAND gate. So instead of this bar, what I am trying to do is, I will short it and I will call it as S. And then this becomes your S bar, right? Same way, I will short another input NAND gate and I will call it as R, and you get here as R bar. And right hand side of this remains same. Instead of R bar and S bar, I have connected it to NOT of S and NOT of R. It is a regular practice to keep S at top, so I have changed from S bottom to top. Okay, so now you can see that how things will change. Now I will put this in another gate like this, another gate, and you will have the same feedback type circuit here. Again, feedback type circuit here. And all of you, please remember, a 2-input AND gate, when feedback comes, it goes as the input of NAND. I have seen many students connecting it to this one wire only. It is a 2-input NAND gate, so it should go as the input of this NAND gate. Okay, so then you will have your S bar and R bar going to this, and you will have your Q and Q bar here. You will have your Q and Q bar for your output now. Now, because there are 2 NAND gates coming, you will see that you will get like this. Okay. Now, because I have 4 NAND gates, we will name it as 1, 2, 3, 4. So this circuit shows that it is SR latch using 4 NAND gates. And in the market, you will get this NAND gate only. In the market, you will get this SR latch using NAND gate only. Okay. Now you will see the truth table of this will also be same as the initial truth table. And if you want, you can analyze it again. You can analyze it again. Let us analyze it. It is good for us to do. So if you have your S and R, let us have again our concise truth table only. Okay, S and R. What will happen? You imagine now. What will happen? If S and R both are 1, 1, what will happen? Okay, okay. Time is up. You analyze it. We will continue with this in the next class. Okay. Fine. SR latch using NAND gate we will see in the next class.